All right, welcome everybody. In this video, I want to take a look at how we can use for loops to construct a bootstrap distribution and then use that bootstrap distribution to construct a confidence interval to estimate a population parameter. So we'll work with the same sort of data that we've been working with in previous videos. So let's assume we have a sample of 20 different golden jackals that we select at random. And for each of these jackals, we recorded the length of their mandible, of their jaw. And we recorded that. And so we had that stored in a vector that we call jaw sample. So you want to make sure that you're all caught up and you've got all of our sample data stored in jaw sample. And now this question is asking me to construct not a 95%, but a 90% bootstrap confidence interval for the standard deviation of mandible length. So in the previous case, we were trying to estimate the mean mandible length. This question is asking me to estimate the standard deviation of mandible lengths. So let's take the code that we used earlier and see how we can tweak it. So here's the code that we used earlier to construct the bootstrap distribution for the sample mean. I'm going to plop that down here in question 6. And now we just want to tweak a couple of things. So I'm going to keep the set seed at 0, 1, 2 just so I get the same output every time I run this code. We're going to still generate 100,000 bootstrap resamples, and I'm going to store them to something just so I don't write over my original bootstrap distribution. I'm going to store it in something called bootsd. So that's the kind of container where we're going to store all of the standard deviations that we get from each bootstrap resample. Now we're going to use a for loop to pick bootstrap resamples and calculate the standard deviation. So we're going to use the same original sample, jaw sample, to pick from. We're going to pick 20 values because, again, our original sample was size 20. So that's why my resamples are all going to be size 20. And I want to set the replace argument to true so that each time I pick a value, I place it back and I'm able to pick it again later. So this is our bootstrap resample. I'll store this in X. Then it's going to go ahead and calculate a statistic. But in this case, we want to calculate the standard deviation. So rather than the mean, we're going to change the function here from mean to standard deviation. And I'm going to store it not in bootdist, but in this new vector that I'm calling boot_sd. So I think that's it. Literally, the only thing I really had to change was the name of the statistic that we are calculating. So in this case, it's a standard deviation instead of a mean. And if I run this code cell, I won't really see anything. This took 2 seconds to run. Just keep in mind, when we did a bootstrap distribution for the mean, it took like a second. This took a little bit longer because the standard deviation is a slightly more complicated calculation. But it took 2 seconds. And in that 2 seconds, it picked 100,000 bootstrap resamples and then calculated the standard deviation of each of those 100,000 samples. And so now we can't see any of that information. So what I'm going to do is calculate the cutoffs for this. So down here, I'm just going to paste this code that we had above. I'm going to put it inside of a set of parentheses so I can see it printed to the screen. And I'm going to call them something different just so I don't overwrite the cutoffs for my previous interval. So now I want to construct a 90% confidence interval. So I'm going to go into the vector where I've stored those statistics, which is boot underscore SD. So that's what I want to calculate the quantiles of. And these were the quantiles that I used for a 95% confidence interval. And so if we want to construct instead of a 95%, a 90% confidence interval, that means we want our interval to contain the middle 90% of bootstrapped statistics. So if we've got 90% in the middle, that means the area in the middle is 0.9. We have excluded 10% of the values, but we split that 10% up evenly in the two tails. So that means I've got 5% that I would have down here, and I would have another 5% up here. So when we use this quantile function, we need to adjust the probabilities accordingly. So the lower cutoff is no longer 0.025, but it's now 0.05. And the upper cutoff I can get by subtracting this 5%, this upper 5% from all the rest of the area. Or I could just enter that as 0.95. So if we exclude the upper 5%, that means we want to find the cutoff that cuts off the lower 95%. So that's where this 0.95 comes from. So I'm going to run this code. It's going to calculate each of these and display them on screen. So now I've got my 90% confidence interval for the standard deviation. So this is telling me there's a 90% chance that the interval from 2.7 to 4.7 contains the standard deviation of jaw length of all golden jackals. And if we want to see this picture that I kind of drew by hand over here, if we want to generate this more carefully in R, we can create code that is pretty similar to the code that we used over here. So I'm going to copy this code over here from the previous question and paste it down here. And we'll just need to tweak a couple things. So the first thing is if I'm going to use ggplot, I need to store my vector as a data frame. So I will just convert the vector to a data frame. I'll call this samp standard deviation. It'll have one column that's going to contain all of the values stored in boot underscore SD. So I just need to create this data frame because I'm using ggplot2. So now the data is stored in df2. The histogram that I want to create is going to display all of these sample standard deviations that we calculated from each of the Bootstrap resamples. I'm going to add a histogram. I don't need to change that. I'm going to add vertical lines. Here I can add one at the observed standard deviation from the original sample that we created. And now my cutoffs were stored in lower 90 and upper 90. I won't change the formatting of the lines. And here I'll just say this is a Bootstrap distribution for the sample standard deviation. And this is the sample standard deviation for the mandible length that we typically denote with an S. So I'll just change the labels on my plot accordingly. And here's a plot of this sampling distribution, the Bootstrap distribution, excuse me, for the sample standard deviation. And you can see here that this is definitely not a symmetric distribution. The center of this distribution is off a little bit from the observed standard deviation in our sample. And this is a case where there is no central limit theorem to describe the distribution of sample standard deviations. So I can't use like a central limit theorem to construct this confidence interval. but we can bootstrap. We can pretty much come up with a bootstrap confidence interval for any statistic using this method. So this is a really, really powerful resampling method.